Hello, boys and girls out there. We meet yet again, this time around to discuss the concept of, again, the modes of heat transfer. We pretty well know that there are three different ways in which heat can be transferred. They are conduction, convection, and radiation. In the previous two videos, we looked at how heat can be transferred through a material, through the process of conduction and through the process of convection. In this video, we will be discussing the concept of radiation. Those of you who missed the videos based on the concept of conduction and convection, please find the links to these two videos in the description of this particular video. Now, when we talk about conduction and convection, it is very essential for us to have a material for the heat propagation to take place. But then when it comes to radiation, there is no such medium's requirement for the heat to propagate from one position to another. The best example, or our everyday life experience where we can notice the presence of radiation, is the transfer of heat and light right from sun until us. Between sun and earth, we believe that mostly it is vacuum. Even though there is vacuum present, heat is being transferred all the way from sun to earth. This is through the process of radiation. When it comes to radiation, we need to understand that there are 7 different types of electromagnetic waves. Now, the reason why they are called as electromagnetic waves is because radiation is transferred in the form of oscillating electric field and magnetic field, as can be noticed very clearly along the yellow direction, that is along the vertical axis. I have the electric field oscillating. Along the z axis, I have the magnetic field oscillating, while along the horizontal axis, that is along the x axis, I have the wave itself propagating. As I just mentioned, there are in fact 7 different waves, that is the 7 different family members of the electromagnetic spectrum, going all the way from radio waves to gamma radiation. It is very important now for us to understand that when we talk about electromagnetic spectrum, we either will have to talk in terms of the increasing order of the wavelength or in the increasing order of the frequency. Here in this particular scenario, the increasing order of the wavelength has been shown, indicating that the gamma radiation have the least wavelength, while the radio waves on the other end of the spectrum have the maximum wavelength. Right, again, as I mentioned, it is imperative, it is important for us to remember the sequence. We go from gamma radiation to X-rays to ultraviolet to the visible light spectrum in between. Now, visible light spectrum itself has the radiation starting from the violet going all the way to red, which means a violet color has the least wavelength and red colored light has the maximum wavelength. After the visible light spectrum comes the infrared radiation, and this is what is of interest to us because it is this infrared radiation which is responsible for the transfer of heat. We need to understand again here that infrared radiation is given out by any substance whose temperature is greater than 0 Kelvin. That is what is being written here. It is the flow of a heat from one place to another by the means of electromagnetic waves. Electromagnetic waves do not need a medium for propagation. Now, it only says that electromagnetic waves do not need. It does not mean that in case there is a medium, will the electromagnetic waves still be able to propagate? The answer is a yes. Even if there is no medium, they can propagate. In the presence of the medium also they can propagate. Now, this thermal radiation or the infrared radiation that I just mentioned is given out by any body whose temperature is greater than the absolute zero in terms of Kelvin. Absolute zero here represents 0 Kelvin, or it also represents negative 273 degrees Celsius if I do not specify the decimal places. Now, any body whose temperature is greater than 0 Kelvin will be able to give out infrared radiation. So what does that mean? Our own body whose temperature is greater than 0 Kelvin, will it be able to give out infrared radiation? The answer is a yes. Right now, if we touch our forehead, we can feel the warmth of our body, indicating that we are giving out infrared radiation. Is the sun also giving out infrared radiation? The answer is again a yes, sun is also giving out infrared radiation. But then we also need to understand that greater the temperature, remember this again carefully, greater the temperature of the body, smaller will be the wavelength of the infrared radiation given out. What does that mean? Our body has a certain temperature, we give out infrared radiation. Sun also is a pretty hot or a warm body, it also gives out infrared radiation. The infrared radiation given out by our body and by sun, will they both be the same? The answer is a no. The wavelength of infrared radiation given out by sun will be much smaller than the wavelength of infrared radiation given out by our body. I hope I made the statement very clear. It is important for us to understand and make a note of this particular statement, because this forms the foundation for greenhouse effect. Right, now higher the surface temperature, as I mentioned, higher the surface temperature and greater the surface area, the more energy they radiate per second, indicating that there are two factors here affecting the radiation, that is the amount of energy radiated per second. What are the two factors? One is the surface temperature, that is, higher the surface temperature, higher energy will be given out. Moreover, the second one is surface area. Greater the surface area, greater the amount of energy given out per unit time, which means warm objects radiate infrared radiation, hotter objects will emit high energy infrared radiation and light. Right. Going by this perspective, going by this understanding, we have, say, three different colors of objects, right? One is a matte black, the other is perfectly white, and the third is a silver colored body. If you notice this carefully, we try to understand this radiation in terms of three major factors. The first one I would say is being an emitter. But in order to understand this emission, let's try to understand absorption. Do we all know that dark colored objects or black colored objects are very good absorbers? Which means if you let radiation incident on a black colored object, that radiation will be absorbed. Now, if there is something which is absorbed, am I also allowed to say after a certain duration of time it will also be emitted? Which means if I have a good absorber of radiation, it can also be considered as a good emitter of that radiation. Now, is it necessary that everything that is absorbed will always be emitted? The answer may be a yes, may be a no as well. For example, if we consider a black hole is a very good absorber. It can also absorb the light that passes close to it. Now that a black hole is absorbing the light, Is it also a good emitter? Will it also emit that radiation? The answer is maybe a yes, maybe a no. Probably right now it is not emitting out that light. Probably right now it is not emitting out that radiation. Who knows? Probably in a few centuries it might be able to give out that radiation which has been absorbed. Which goes on to say we have a condition for a black body. I'm not talking about a black hole, I'm talking about a black body. A black body is any body which is either a good absorber or a good emitter. A black hole can be considered as a black body because it is a good absorber. At the same time, sun can be considered also, as a black body, not because it is a good absorber, but because it is a good emitter. I hope you understood the difference here between an absorber and an emitter. Whether the body is a good absorber or a good emitter, that particular body can be considered as a black body. Apart from absorbing and emitting, there is yet another property, which is the property of reflection. Now, there is radiation incident on a specific body, and it is a good absorber, which means it is able to absorb. Does it then automatically mean that it does not reflect anything at all? Alternatively, if at all I consider a body which is a very good reflector, it then means that it cannot absorb anything and therefore it cannot emit anything as well. So, all good reflectors are extremely bad absorbers and therefore bad emitters. At the same time, a good absorber is considered to be a very bad reflector of radiation, which means in winters, if you go out, you would better wear dark colored or black cloth. Black clothes, not cloth, but black clothes. Reason: black is a good absorber. The little amount of heat, infrared radiation that is present outside, you will be able to absorb. But then in summers, you better wear silver colored or light colored or white colored clothes. Reason: they are good reflectors. There is already plenty of heat outside, plenty of infrared radiation outside. You might want to just reflect it away. You do not want to absorb it and make your own self feel uncomfortable. Which means in hot sunny countries, the houses are actually painted white to keep them cool inside. Reason, as mentioned already, white or silvery surfaces are poor absorbers. They are good reflectors. They would reflect away most of the heat or thermal radiation that is incident on the rooftops. If I need to compare the absorption of two different bodies and check whether, hey, you know what, this black colored surface is actually a good absorber, what we can probably do is have a heat source, place two surfaces, one which is colored in black and other which is a white or silver colored object, place both of them equidistant from the heat source. The surface area of both of these objects should be the same, and as mentioned again, equidistant from the heat source. Place thermometers and measure the temperature after a specific duration of time. If you are able to follow these norms, you will automatically get to know that the thermometer placed near the black colored object, the temperature there will be higher. As mentioned, to make it a fair test, the surface area of both of the plates must be the same. In fact, the nature of both of these materials also should be the same. Right? The distance between the plates and the source of radiation must be the same. The radiation source must be the same for both the surfaces, and finally the surface which shows a higher or a greater rise in temperature is a good absorber. Consider this in the frame of mind of an IB MYP criteria B question. All right, you might want to list out all the control variables. You might want to list out the independent and the dependent variable as well. Now that we have observed or compared the absorbers, how do you think we'll be able to compare emitters? In the case of emitters, there is a particular device called as the Leslie's cube. Kindly do some research with regards to what a Leslie's cube is, and you will get to know that it is a six-faced cube having the same surface area. Since it is a cube, all the sides will be the same. Therefore, all the six sides will be having the same surface area. This is in fact a cube which is empty, hollow from within. Therefore, we can fill in this particular cube with hot water, metal cube containing boiling water so that the temperature of the substance present inside will be maintained the same. Each of the face here has a different color. Say for example, this side here as mentioned is a painted shiny black. This side is painted dull black. On this side I have shiny white surface, and on that side I have a dull white surface. The moment you now pour this hot water or boiling water, each and every surface is being provided with the substance with the same temperature. If I actually try to measure the temperature from each of these sides, we will get to know that the shiny black surface will emit the maximum amount of radiation because it is black is a good absorber, or rather it is a good emitter. Right, to make it a fair test, the temperature of all the surfaces should be the same. How are we making the temperature of all the surfaces the same? It is by pouring hot boiling water. The distance between the detector and the surface should be the same. The area of surfaces should be the same, and hence we are considering a cube. The surface for which the thermal radiation detector shows the maximum reading is therefore the best emitter. In this particular scenario, it is the shiny black surface which will have the maximum temperature reading. We have yet another methodology through which we can investigate how fast how fast a substance can be cooled. We have the cooling curve here, investigating the rate of cooling of water. Now we need to understand whether it is a comparison of emitters or the comparison of absorbers or the rate of the cooling curve. These are all various aspects through which we can test criteria B. This is specifically for IB MYP students. There is a list of control variables that is being provided to us already here. What are they now? It is the room temperature, that is the ambient temperature should be maintained the same. The initial water or the starting temperature of water should be the same. The volume or the mass or the amount of water present with us should remain the same. The same type of thickness or the material or size of the volume of the beaker should be the same. The time delays during the operation, so that is, we will measure the temperature at equal intervals of time. Not only that, we need to ensure that either there is a steady breeze flowing throughout and that should be maintained constant, or there should be no flow of breeze at all. This way we can certainly determine, or we can get to know the readings with regards to how fast water can be cooled down. So these are some of the factors that would affect the rate of cooling of water. If the difference in temperature, that is, the ambient temperature is kept the same, but the temperature of water is being changed. Say for example, I start with an initial temperature of say 90 degrees Celsius, while the temperature of the surroundings, suppose it is 20 degrees Celsius. In the next experiment, suppose I now consider water which is present at 75 degrees Celsius, while I continue to have the same ambient temperature at 20 degrees Celsius. Clearly says the greater the difference, the faster the rate of cooling. In this scenario, the temperature of water when it was at 90 degrees Celsius, the rate at which it will cool down will be faster than in this particular scenario. So one factor that would affect the rate of cooling would be what? It is the difference in the temperatures. The second factor is what now here? Greater the mass of water taken, greater will be the rate of cooling. 100 grams versus 1 kg, it clearly says that the 1 kg water will cool down faster provided both of them are having the same initial temperature. The material of the beaker will certainly affect the rate of cooling. Hot water will be cooled down faster in a copper beaker than in a glass beaker. Reason: copper is a good conductor of heat energy. A beaker of larger size indicates that the surface area of the beaker will be higher. There is a higher surface area of the liquid exposed to the atmosphere. Therefore, it will cool down again faster. If there is a continuous air flow present, then also we can cool down the liquid faster. A continuous flow of air indicates that the moisture that got accumulated over that particular region will be carried away. Therefore, the cooling will be faster. I hope all of you got a very good idea with regards to how, or rather, what are the various factors affecting the rate of cooling of water. With that, this is what we have for the concept of radiation. I hope all of you understood this. If you liked it, subscribe and share the video, please. Thank you, everybody. Goodbye.